Here we'll use Gauss Jordan method in its classical form to find the inverse of this matrix. We start by rewriting the matrix A, and then creating something called augmented matrix with the identity attached to it on the right. Identity, of course, has the same size, 3 by 3 in this case. And in the Gauss Jordan method, whether it's classical or not classical, the goal is to use elementary operations to create an augmented matrix with identity on the left. Then whatever remains on the right, if it is possible, whatever remains on the right is going to be the inverse that we're looking for. The classical Gauss Jordan method goes in two stages or two steps. The first one is to create an upper triangular matrix on the left with ones on the diagonal, zeros below it, and whatever else above it. We move along the diagonal element by element. The elements on the diagonal are called pivots, and we're changing pivots into ones and using those ones to eliminate, using elementary operations, every entry below that pivot in the column below that pivot. We start with the first pivot, the top left, the position 1, 1, but it's a 0. We cannot use a 0 to eliminate anything. So we need to first interchange that row with the first row that has a non-zero entry in that pivot column, which is second row. Right? It could be, potentially could be any, but in a classical Gauss Jordan method, you choose the first row in that pivot column that has, the first row below that pivot entry that has a non-zero entry in that pivot column. So here we interchange row 1 and row 2. Now we can use that pivot to eliminate everything below it. Now you have a 0 in the second row already, so you need only one operation to eliminate this -2 by simply adding 2 times row 1 to that row 3, because -2 plus 2 times 1 is going to give us a 0. The first row is unchanged, so I am copying it. The second row is unchanged, so also rewrite it. And then the third one will change. We have -2 plus 2 times 1, which is 0. 1 plus 2 times -1, which is a -1. -3 plus 0 is -3, 0. Here you have 0 plus 2 and 1 plus 0. We move on. The next diagonal entry, this becomes our pivot. First thing you want to do is you want to change it into a 1, so you divide the entire second row by 2. And that's a simple operation. First and third row remain unchanged, and the second gets divided by 2. Every entry of the second row gets divided by 2. And now we can use that pivot to eliminate everything below it, change it into a 0. There's only one entry below it in row 3, which you can simply change to 0 by adding to it row 1, because -1 plus 1 will give you a 0. First row is just rewritten, nothing changes here. Second row, the same thing. And the third one is changed by adding to it row 2, which is a 0, 0, -1, a half, 2, and a 1. And now one more step, the -1, the next pivot, you have to change it into a 1. Simple operation, just multiply the entire third row or divide it by -1. Now that ends the first step, the first stage of the Gauss Jordan method. Now we're going to go in the reverse direction. We start with a pivot at the position 3, 3. There is a 2 standing in the second row, so the second row has to be changed by subtracting 2 times our 3. And then there is a 0 in the first row, so no operation needed. First and third row remain unchanged, and the second will be changed by subtraction. So 0 minus 0 is, of course, 0. 1 minus 0 is 0. 2 minus 2 is 0. A half minus 2 times -half gives us 3 halves. 0 minus 2 times negative 2 makes it a 4. And 0 minus 2 times negative 1 makes it a 2. And the third row remains unchanged. Okay, and then one more step. Next pivot, one entry to eliminate right above it, the negative 1 in row 1. So R1 can be simply changed by adding to it R2. The third row remains unchanged, so I'm going to start with rewriting that. Second, the same thing, so I'm going to rewrite that. And then the first changes by addition, so 1 plus 0 is 1, this is 0, 0, 0 plus 3 halves, 1 plus 4, and 0 plus 2. We got an identity on the left, so whatever remained on the right is our inverse matrix. So just to complete the problem, let me copy that, the matrix on the right, no transpositions, nothing, just as it is. This is our inverse matrix, which of course can be always checked by multiplying A times A inverse. You should get identity.